Okay, good morning to everybody. We'll continue. So my hope is to be done with this by the Christmas break. I mean, we certainly must be done by the Christmas break. Otherwise, it's not it's not a proper summer course. so so we were looking at this 2-point invariant. So this is what? This is some kind of curve count, and that is this is like an operator, so it's an endomorphism of current K3 of X. But since its definition requires localization with respect to action scaling the domain, so this was some sort of localized thing. And so this depends on two kinds of variables. On the current variables. So first the current variables. And thus we can choose inside a maximal torus on the automorphisms of X. And also what people call the Kähler variables. We call it Kähler variables. Z, this live in peak X tensor, well, C star if you want. So this means when we count quasi-maps, we put the weight Z to the degree of the quasi-map. That's this counting. And what we've shown last time, and they satisfy, so this thing, this object is the fundamental solution. Solution to 4 or maybe 4 for a flat Q difference connection. Right, it also depends on Q. Okay, so this is a Q difference connection in both sets of variables. And so our goal is to identify a particular direction in that connection today, and then talk more about how this. And so here instead, inside of T, we will choose A. So this is preserved. So if I have a torus, all my varieties are such that the symplectic form unique up to multiple. So my torus has a character H bar. This is the weight of symplectic form. This is how it acts. H bar is the weight of the symplectic form. So it's a character of a torus. And then we will look at the kernel of that map. And so we only will shift, so in this course in general, we'll only shift variables that preserve the symplectic form. Shifts in these variables. So we don't attempt. We don't attempt. Maybe I'll do not attempt. Take H bar and send it to H bar times Q. I mean, it is possible. It's possible. So this is not very complicated, and this is not needed for, as far as I can tell. I can't see an immediate application for difference equation like this, because this is some. If somebody wants to study this equation, that's fine. But this is possible, but very complicated. very complex. And so this is like what? This is the simplest possible example of this. One of the simplest example of this theory is this Chernigov-MacDonald theory. And so this is like the operator which take T to T times Q in MacDonald. So there such intertwining operators do exist. People do people do use them, but for certain things. But it's not. It's very difficult to construct, and this is very. So like I said, this is seems there's no good. Other than the existence, very hard to say something about them. But if anybody wants to study that, it's certainly, I'm sure there's the treasure of interesting things to discover. But it's just too complicated. But so also it's like taking UH bar and sending to UH QH bar. So this is okay. That's, one can study such things, but it's complicated. So we know this is too complicated for us. And so we just focus on this torus A. So this is A, we consider versus this torus Z, which is just where the pick X all times C star. Well, maybe if you want it very canonical, all times over Z. And so this is, we would like, so today the Knizhnik Zamolodchikov, we want to talk about QKZ, the Knizhnik Zamolodchikov. Those are very special directions here, correspond to very special co-characters there. And we will, so before we talk about those, I'd like to have a general discussion on this. And so then one can start by discussing where are the singularities, what's the location of the singularity of this equation. So location, the first thing to ask, first question. Where are the singularities? And it's best to ask it mod Q. So it's really we take a torus and we wrap it around on the elliptic curve. So these are the kind of periodic picture you can see behind me. So this is the question. And why is it mod Q? And what are the singularities? So if I have a difference equation, let's say in one variable, if I have some variable innovation, QA equals some matrix S A. It can also depend on Q. Then if I then the singularities are the points where the determinant of that matrix is zero or infinity. So this means where the matrix is not. So where is or maybe where the matrix is not in GLN. So this is not if it ceases to be regular or inverse is regular, then it's that means we have a singularity. So this is a singularity. And so then if I have one of these equations, and then maybe I'll plot the logarithm of A, then in the logarithmic plot, if I have one of those singular points, then of course if I just propagate my solution, then I also get, then its solution will have the singularity of the point QA, Q square A, and so forth, right? And also if I make gauge transformation that takes singularity and shifts it by. So if I have singularity, if I make a gauge transformation and takes it and shifts by Q. So gauge transformation means I pre-compose and post-compose with the matrix, but that matrix will have some singularities, and then it can, but except it will be shifted by Q. Pre-compose and post-compose cause different equations, so that will shift it by Q. So that makes sense about draw the singularities both both in logarithmic coordinates and also take a mod q. So think of this as periodic. So the singularities, we'll think of a periodic or some locus. Think of the locus, kind of a singular locus. Think of the singular locus. Locus in A mod QZ, Q to the, and then mod Q, not QZ, it's just mod Q, so mod Q co-character. That is just our old friend, that's the elliptic homology, L equivalent to elliptic homology point. So, and the answer on this side, on the side, now I maybe copy this picture. Maybe it's not so easy to copy. And so this is now a picture of, I think of this as a picture of elliptic, equivalent elliptic homology point. Because some torus, and in this torus I have hyperplanes. I have a pair of hyperplanes. So these are shifts of codimension 1 subtori. So these are shifts of, you take L A prime of a point where A prime and A is codimension 1. And so what is, we have seen this arrangement before. This is an arrangement. This is an arrangement. This is an arrangement of where something happens to the fixed locus. So if this is over this, we have A equivalent to cohomology of X, with the fiber being the cohomology. So if I have a point A here, then the fiber here is like the cohomology of the fixed point. Right? And so when this means where this fixed locus changes, so this means these guys are the hyperplanes are, so these are the points. Points H such that the fixed locus is not equal to the fixed locus of the whole torus. And so this is right. And so another description of that is that, so maybe I'll use the whole horizontal space, and we'll come to the Kähler roots later. So another description of that is the following. Then we can take, we look at the fixed locus of the whole torus inside X, and we look at the normal bundle to that. So this is, consider the normal bundle and to the whole space, to the fixed locus of the whole space. So this will have this will have some weight. So this is there's an action of A here, and it will split according to the weight. So A doesn't act on the base, so it will have some weight appearing there in that bundle. So maybe if the weight, if WI's, so then maybe you take the collection of WIs. These are the weights of A in this normal bundle. And so this way, so this is the sit. This is a picture in the torus, and these are the picture in the character lattice of the torus. So there's a character of A, some subset. So this is not belong, it's a subset. And so then my hyperplane arrangement is so periodic. This arrangement, which I can think of, this is a periodic arrangement. I can think it takes place in the Lie algebra of A. So then my arrangement is just, okay, maybe I'll copy it here. This is arrangement. These are the points. Since it's a Lie algebra, maybe I should denote it by a point in the Lie algebra. Maybe I should denote by a Greek letter. Let's say xi. And these hyperplanes are such that xi pairs with one of the double i's, and that is an integer. So what does it mean? What does it mean? Some element has. So this is the map from here. Remember from the Lie algebra from the torus. This is the map that it goes to the point A. It's exponential 2 pi I xi. And so this acts trivial on some normal bundle if and only if this pairs to an integer. So that is the hyperplane arrangement here. And then so maybe to be a little bit more precise, we have, if we look at the fixed locus, if this is my fixed locus, then the weights in the normal bundle, since I have a symplectic form, they appear in pairs. So there is if for every weight W, there's a dual weight, which is 1 over WH bar, which is the weight of symplectic form. And so these hyperplanes, if I look at them closely, they in fact come in doubles. So this means in my pause it. So maybe let me color this weight blue. So this for every weight here, there is exactly a parallel like this. So meaning that for every hyperplane of the form where W, the value of W times maybe Q to the N equals 1, there is a parallel one, which is where you have W H bar Q to the N equals 1. And here we think that maybe H bar is about 1. And the reason is it's good to think as the H bar, in this picture I wrote that H bar is roughly 1. And the reason it is good to think about H bar as being roughly 1 is because at H bar exactly 1, everything cancels. You get all the poles, all the zeros cancel. So these two guys, these two, one of them is a pole and one of them is a zero. These two exactly annihilate. really equal h bar is 1. So when the h bar, I don't know if I emphasized it before, h bar is a variable which plays a very important role for us in that we don't really deal with it directly. We don't really, we don't work with it. The definition of stable envelopes doesn't involve h bar. The difference equations which we consider do not involve h bar. Well, I mean, they depend on the bar, but don't shift h bar. Well, for reasons I explained, we could have, but it's too complicated. And so, then, however, if h bar was not there, the whole theory would be trivial. So if there's all this count of this cross counting, that'd be just trivial theory if h bar was equal to 1. So this is it's very important that it's there, and it's important for an application that it's there. But it's if it weren't there, then of course we could have developed the whole theory, but all the curve counting and everything will be just some trivial answer. And all this equations we consider will be equations with constant coefficients. So that would be not so interesting. So it means this equation have zeros and poles that exactly cancel. So if I remind you that this is if you remember we had the expression or h bar is 1 or h bar is q to the n, q to the q. In general, if it's some power of q, then you get something trivial. Right. So maybe if I remind you when we had the hypergeometric function. So for P1, this kind of vertex function for P1, it had the form, it had summation over d z to the d. Here I have q to the d, maybe q a d. Here h bar d. Here h bar a d. And so if h bar is equal to, the easiest substitution, if h bar is equal to q, then this becomes really silly. It becomes a geometric series. So it has no singularities of any kind. Well, I mean, it has singularity of 1, but it's not the kind of a silly singularity. Okay. So this, and more generally, if h bar is some power of q, this becomes a rational function. Right. So those are the singularities, and so maybe I should say that this W's, this defined this weight W's that define the this arrangement, this may be called we call this W's. This set. This is some finite set. This is some finite set of characters of a torus, so it makes sense to call it roots, and this may be called equivalent roots. Roots for x of x, maybe. And then on the killer side, so when we come to the killer side, there will be killer roots. So this will be a finite subset in where? So in characters of my killer torus this, but these characters are nothing else but h2 of xz. So these are curve classes, some finite collection of curve classes that will play a role similar to what we have here. And we'll get there after we discuss the covariant equations. And so and why it's kind of remarkable that there is this structure, and then maybe but what you see in my background, and maybe I'll put here now in the discussion. So insert the picture. Oh, let's see if I can succeed with that. Right. So this is if you take the scalar roots and the covariant roots, they're supposed to. So if I have they live in spaces of different dimensions. So if I take we call this would be if these are covariant roots for x, and these are the scalar roots for x. Then there is this remarkable symplectic duality that will just, well, it will exchange the equation. So it will exchange two connections. One connection will become it will take two different connections and exchange the roles of a covariant and scalar variable. So this would be to some kind of mirror, and this is some mirror here. And so this two sets of roots better have the exact parallel properties, and so it's kind of remarkable that this is how this works. Well, we'll get to that at some point. Maybe not in this course, or maybe the summer course of 2021. So so going back to the equivalent roots, so now we have among all different equations, in equivalent variables, we want to find QKZ. That's what we started. That's what we started last time. So recall. So this is what was the QKZ look like. So the QKZ is an equation of the following kind. So if I have maybe function, let's say of two variables. So I just explained it's enough to do it QKZ in two variables, because everything else you can, if you have any other shift, you can group it in a shift of one group. So you can take a shift of one group of variables and another group of variables. This will generate the whole thing. So that's maybe we'll stick to that. So if I have QA1 and then A2, this is some operator Z acting in the first factor, then the R matrix of their difference, and then psi. Well, so that's the QKZ. Okay. And now, did everybody remembers what happened last time with the QKZ? Anybody has problems with transitioning from general discussion to the specific equation? All right, so don't be shy. So what we see, and remind you the meaning. So this is psi is the kind of thing we consider. So this was supposed to be. So this was supposed to be the shift operator here. So maybe I'll move. One of my devices is beeping very in a very suspicious way, but I guess it'll be for the rest of the lecture. The device will be beeping. But so this was supposed to be the shift operator as sigma. And how was that constructed? So this is it had the meaning that I had this was equivalent. This was some count with two relative points, but then shifted by this twisted by this co-character sigma, right? And then here of course, as usual, we count with z to the degree, as usual. Okay? And so now if we look at this equation, we see very surprising facts. There are, in fact, several surprising facts. One is that z appears only here as an overall, as a factor. Only outside, only outside, and as a monomial. So this is very surprising, right? So this is, I mean, in general, if you found this was supposed to be, so this means this object. So in principle, it's a formal power series in Z. And that formal power series in Z is in fact not even a polynomial, it's monomial, in some sense monomial. So okay, we'll deal with that. Interesting. So we already discussed that Z doesn't appear here. So this is, so okay, we know that there is no Z in this, but maybe more importantly, there is no Q in this. So Q, there's no Q anywhere. So this is, if you used to sort of a classical treatment of Knižnik Zamolodchikov, maybe I make this remark. So so classically in like Frankel Rashetichin and many other sources, the Knižnik Zamolodchikov is derived in the context where Q is tight. So there's have Q is something like H bar to the power level, or something like that. So this is an equation, some vertex operator, some stuff. This vertex operator acts on representation on representation of some given level. So this is like H bar to the level. So this Q and H bar are tied with one another, but here we just don't. I mean, Q is just free. For us, Q is free. I'll write it here. Q is just some variable. I mean, you can work on some kind of generic level. So anyway, it's a variable. It doesn't appear here. And so what does this mean? This means that let's see if I paste now, then what will come out? Oh, okay, cool. So this is good. So it means what? Means if I have some difference equation in which, so in my difference equation, only if I go in the direction, so this is, I have a one parameter, one parameter subgroup. So it's somewhere in my, so I have some, maybe this is the direction of sigma, and let's say this is the origin. Say this is the origin. Okay. Then if I go in this direction, I should only get here psi. It's only singularities. At what? At so it has some whatever singularities it had in a kind of well, here this kind of at one and just powers of q, if you will. Something at q to the n times something. which is not what does it mean? It's not typically happens. So if I have some weight, so if I have some, like if I, yeah, typically, not the case, right? So if I have, so this is sigma of, so to speak, C star, right? So why is it typically not the case? Is because my singularities occur is where W. So if I have some, if so my, so if I have so like in this picture here, let's suppose I have a character of my roots, maybe call it W here. If W pairs with my sigma to some number n, then means I get singularities at all n roots of Q, right? Because I mean that has to be the case. So if I take, what does it mean? I have some sigma. Sorry, what does it mean? That W of sigma of some variable, whatever, call it A, maybe not A, let's call it B. So this would be, so this pairing means I get B to the N, and so I get, so Q to some M, maybe M. I apologize, I should have thought about this notation. Then this is going to be B to the N, Q to the M, and so this means I get the shifts, so I get the singularities at Q to the power 1 over N times Z. And so this means if I have something like this, it has to be the case. So it has to be the case that if I pair my sigma with any root, well, of course it can pair 0, but otherwise, if it's not pair 0, it could be plus or minus 1. So this has to be less or equal than 1. Have this condition. Such condition is very well known in Lie theory. So if I have a co-character, so in general in Lie theory, if I have a co-character and it pairs to at most 1 with every root, such a co-character is known. I mean, it has a name, and then this means sigma has to be minuscule. It's by definition what this means. So this means, by definition, means minuscule co-character is such that pairs with every root at most 1. Okay. Following so. This is definition. This is the definition. This is Lie theory. Actually, it's easier for us. It's easier to have an equivalent, and it's somehow easier to establish an equivalent property of minuscule characters. Is that, well, if I think of let's think of, say, my example of, if I have some, my x is something like, so in this example, is something like T star P1. And then I know it's not a very complicated example, but it's good. It's good to have it. And then, so this is resolution of a cone. here. And so I have my torus acting, preserving symplectic form. I have a co-character of that torus. Well, it means it'll be some, will act with some weight sigma here. Then since the preserved symplectic form will be sigma inverse, and then since this is P1, it will be sigma, and then it will be sigma inverse here. Right? And so this, looking at this picture, if I have an action, or maybe, sorry, maybe I got a little carried along myself. Let's think about the root. So I have some weight. So maybe I'm really worried about the device beeping, but I hope it doesn't explode. So if I have some weight, maybe call it W, and then so there's a W inverse, there's W, and there's W inverse again. So then, so what does this diagram show? That if I have some normal direction to my fixed locus, so this is my XA, this is my X. If I have some normal direction, this normal direction may or may not project non-trivially, may project trivially to the base X naught, may project non-trivial. So this is, there are two options. Here, the first one seems to be got to be project non-trivial, but this one is collapsed. Now this is collapsed. But if it is collapsed, then it means there is a P1, there's a P1 of that weight, and that P1 will have to have the other end because it's collapsed to the base, and so the fibers of this map are proper. And so if I have a line of a certain weight, then this line will have to be P1, and this P1 will have the opposite weight at the end. So this is the weight of the this collapsed orbit, and that orbit will have the other end of the same. The orbit. And so then at the other end, this would come, this weight. So now, since this is again symplectic, then this weight eventually will come out. So every weight of the symplectic form eventually will appear in the weight of X naught. So this will be, well, even though some of them are collapsed, but there are at least some of the weights will appear in X naught. That makes sense. And so this means that this means what? What does it mean, X naught? It means X naught is embedded into a vector space on which my torus, so the minuscule condition is that on this vector space, my torus sigma acts with weights plus minus 1 or 0. But what does it mean? I have a X naught embedded in some vector space. This vector space is, after all, these are the this vector space is generated. You can take the functions on this vector space. Functions here, they're what? They generate global functions on X. On X naught, and which is the same as functions. Right? So then I can decide. So this is one can say a more convenient definition. So maybe definition prime sigma is minuscule if global functions if functions on x on x node, so maybe I'll write c of x is generated by functions of weight equal 0 plus minus 1 with respect to sigma. Okay, and that is very, this is much easier to check because this is, for this we have an access. This is my first fundamental theorem. First fundamental theorem of invariant theory. That usually gives us generators, for instance. So if I have, so then it's an exercise. But if I take the co-character of the form, so my co-character has to be so sigma of some variable, I think we denote B, and so this has to be a matrix, and I'll take it to be B, 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 and then 1, 1, 1. This sort of thing. This kind of expression. This sits in the GLW, and those are incidental. These are fundamental. This is kind of fundamental. These are minuscule for. If you remember what are the minuscule covariates for GLN, there are this. So meaning Q for GLN. So we could take this. So this says this is in particular, this is the framing. This is an automorphism of Nakajima variety. Preserving the supply form. So that this is, the statement about this is minuscule. All right. So this is at least it doesn't prove that the corresponding difference equation is QKZ, but it has means this corresponding difference equation has a chance to be QKZ. So this is, to do this exercise, you just remember, so what the first fundamental theorem says. We have some invariants of general linear groups. So Nakajima varieties are by definition are quotients by general linear groups. All invariants for general linear groups are generated. You take all possible tensors and contract all possible indices which you can contract, and so those are the invariants. And so then, okay, this is you see that this is very true. This is not hard to see. So I invite everybody to do this exercise. But anyway, I have the chance to be QKZ, and so we can now forge ahead. And so now we have to see where is this minuscule condition gonna come. This has to have somehow come up geometrically, right? So this is now going back here. So maybe we'll look at this expression. I'll copy it here. So this is about the cube. And then after, I think one day before pandemic is over, I will master all this kind of hand gestures in OneNote, but that day is not here yet. So I'll just take this, copy it, and then put it here. So going back this here, back to this. Now, of course, we look at the most mysterious thing is this part. That's the mysterious thing. So maybe I'll circle it some number of times. So we'd like to look here. And so what is this? This means what I already tried to stress it before. So that what will be the fact that this is monomials? This is just really, this comes from, so it means only constant map contribute. Quasi maps. So this means this z tensor 1, that is really z the degree of the constant. So if I have a one parameter group, it will have some fixed loci, and then the degree of the and then the twisted geometry will have constant maps, constant sections, so to speak, constant section corresponding to every component of that, of every component. This has a bunch of components. This is some locally constant function. On components of this, and then and this is the function we computed and we identified for this. So this is something we computed last time, and then we started doing. So this is something we spent some time doing, and so now this is so we need to show that only we need to have some sort of mechanism by which all other contribution will cancel, and so in all other contribution will cancel from, so as I stressed many times, all other contributions will vanish. And the reason they will vanish, the way to prove it is by rigidity. I stress the importance of this. It's not how I spell rigidity. I stress the importance of rigidity type of argument many times in this course, and as Igor did in his lecture, so it's really important argument. The way it's done, and in the way here it's in equivalent K theory, so this will be done in two steps. So rigidity has two arguments, so this has to be the confluence of, you have to prove some properties. Plus you need to bound the weight. And of course, the minuscule condition, that sounds like a condition about the weight, but it also will play a role here. So minuscule is important for this properties, and I will now explain it in the simplest possible example. Okay. So this is okay. If you lost in some woods of neural geometry, you can now come to a little clearing. It's like a little clearing in the forest. So this would be a silly example, but it will explain what's going on. So then we'll take X to be the simplest possible symplectic manifold one can imagine, just C2. And then the sigma, I think we denoted B, this will be B to the K 0 B to the minus K. That's preserved symplectic form. So this is in the morphisms of X symplectic form. So what does it mean twisted? So if I have this twist, what's that? This means I have X bundle over P1, so my 2 is P1, and then I have twisted x, which is, so now I have a bundle. Maybe I should have drawn the P1 smaller or x bigger. Let's start with x. And so x will be a twisted bundle. So it was a non-trivial C2 bundle or P1. So this is now this maps to P1. So now I'm draw it like that. So this is P1 and have a map to P1. And so that X is the total space. This is my space X is the total space of O of K plus O of minus K. Right? Now I want to study. So now we want to do, now we're interested in sections of that. So this would be, everybody's on board with that? So what does this section look like? Well, the sections, there's the negative. So this is the, of course, the by this mnemonics I described it, the negative one is called, this is O of minus K. Well, let's say K is positive. Let's say K is bigger or equal to 0, or maybe it's just bigger than 0. So let's not waste our time with 0. K is bigger than 0, and so then I have, this would be O of minus K, and this is O of K. And so O of minus K negative bundle has no sections here. No sections here, but there's O of K has plenty of sections, so this would be like a K plus one dimensional space of section. These are all possible polynomials of degree K. These are all possible. And so, but somehow, if we wanted, so as I said, rigidity requires some kind of properness, and this well, not some kind of, but actual properness. Somehow, this is bad for properness. Right? I mean, this is really so vital. It's a vector space, but another degree K. This is not so good. But so this is what I can do, since I'm think of this as an operator. So since we think of this as an operator, we can construct, since we can do is we can restrict the values of the section at 0 and infinity, because this is just to set, we were thinking of some operator, so we take a matrix. So this means by taking matrix coefficients. So this is some by pairing. So it means instead of some operator, and then we'll take some class on X, some class another class on X. Well, the K theory of X one-dimensional, but so you can imagine those. In general, X has some, it pairs these two things. And so what would you like to do? So maybe first, your first idea would be that, okay, maybe I should just set it to just fix it to be a point. So if I fix it to be a point, so we can put a point there. And then, oh miracle, if I put this point condition, then if K is exactly 1, exactly in the minuscule case, so this is then 2 cases. So I have somehow two cases here. So if k is bigger than 1, I have polynomials that vanish at 0 to infinity. They're still k minus one-dimensional space of this. So I can choose an arbitrary polynomial that vanishes at 0 to infinity. Maybe this is. So these are the sections. Here I get sections of O of k minus 0 minus infinity. There is a k minus one-dimensional space, which is still not proper. But if k is exactly 1, then I get there's really no sections. No, 0 section. K is exactly 1. Your only possibility is to have 0 here. It's really 0. And this is proper. And this k equal 1 is the minuscule condition. Okay? So this was the first approximation. So first approximation. So why is this not an excellent thing to do? It's not an excellent thing to do because not great when we will start counting weights. So then this means if I when we take, so we have some proper integral, in the end we would like to show that in fact that proper integral is, well, first we show it's constant and then we show it's 0. So this means, or you can go it in one step. So this anyway, somehow the way you prove something is 0 is the way to prove that this is some result is some, first the properness gives you the result is some Laurent polynomial, and then counting weights means you so this is, maybe I'll go back here. So this is properness bound the weights means this is properness tells you here. See if I can do it. Okay, this tells you that the result. This tells you the result is a Laurent polynomial, and then tells you that the result, the Newton polygon of that Laurent polynomial contains no lattice point. So the result of computation occurring in K-theory is some in principle. So we compute in localized first. So it's some rational function. Then if it's proper, then in fact it's actual computation, actually occurring in K-theory. So its result is Laurent polynomial in some variable, some set of variables if you want. And then bounding the weights means you bound the Newton polygon of that Laurent polynomial, If that the Newton polygon is found to contain no lattice point, that means the result is 0. So that's how you argue. And so then, so this is when we get started to count weight, well, it means we spend too much. What is the point? So if I take like the over point, this is, so if I have my I call this my C2, and it's already in a minuscule situation. I have weights B and B inverse here. Then O over point, that has 1 minus B inverse 1 minus B, right? So this means the Newton polygon of that is kind of like that, right? So this means the Newton polygon of that goes from -1 to 1. And so this is about twice as much as we really need it. So we can do better. And the way to do it better is to take this thing here. So, and instead of doing a point, I'll put the repelling direction. So this means I take kind of that thing. So I take the kind of attractive with a minus sign. So this is something which is repelling for my action. Yeah. And so this means this whole picture is still still proper, but now but this is the fact that I'm allowing. So this is now I'm allowing. In principle, I'm allowing the endpoints to go in this direction, but this means so one can't go. So in this direction, one can't go. Curve. The section can't go in this direction anyway, because it's negative, right? The corresponding direction, the normal bundle negative, has no sections whatsoever, and so this can't. I mean, it's okay to allow it's okay to allow the endpoints go in directions which can go anyway. So this is very popular in like management. You you forbid things by other means, and then you allow certain things. You're being gentle. You allow certain things which are forbidden by other mechanisms. So that's not only in mathematics but also in human life. You see it all the time. Anyway, that's the idea. Any question about the idea? And so now the implementation, you will think that maybe this is really a silly example, but its implementation for general X, its implementation is the part about properness. That's really so for general X. We have what? We have the map X going to X naught. This is proper. And then X naught by hypothesis. This is embedded, also proper. It's just embedding proper to a vector space. Let's wait. 0 plus minus 1. So then if I take if I take this kind of twisted sigma, maybe sigma twisted. So this is where this minuscule condition comes in. This is where it comes in. And so then so that means that this sigma twisted quasi-maps, sigma twisted quasi-maps to X, they go, so this would be decomposing this. Just take a quasi-map, it has some evaluation, we can just push it forward. I mean, so maybe just evaluate. So this will be a proper map. So the sigma twisted quasi-maps to sections. To what? To sections of a whole bunch of 1, of -1, and no. Right, so these are twisted quasi-maps. This vector space. Okay, the vector space is okay. We just did the example, and so then it's so this is fine. So that's, and so this is, we decided that this once we impose, we just did properness here. Properness here is like in this little example. And so this being proper, the whole thing's proper. Okay, so that's how you use minuscule condition to prove that something's proper. And so now we can do the following kind of theorem. That if we take, so what we can do, we take the fixed locus, and then we have our x. Here we have this operator we'd like to understand. Is this the operator S sigma? So this is what we'd like to understand. And then it's an operator here. It's a bit. Yeah. So I write it's not an operator from X to X. It's some correspondence and moreover slightly localized and so on and so forth. But anyway, it's an operator. So maybe I'll denote it by its proper names. Something like that. This sort of operator. And now, what's the idea? The idea is we decided we need to put two negative things. Right. So this means here. So in this picture here, or that picture. Oh, yeah. I have some centering issue, which I'll have to correct later. But so it's another feature of OneNote is remarkable is that how it doesn't really have the paper is really endless. So you have to make sure you stay in there. You don't go out of bounds. There's no. You can't get to set. I don't know how to set the size of the paper. If anybody knows how to set the size of the paper, that'd be priceless. So this is so what we did here. We decided that we're going to put in the direction which are negative, which means repelling directions for us. In those directions, we might as well take attracting manifolds or more general stable envelopes, right? So that would be the same type of thing. And so but in the direction, like I said, in the direction which are negative to where we want to go, just compared to what we want to go. And so here we would say, so okay, let's do here and put the stop kind of minus, and that stop has to be taken at some. So this means minus means has repelling directions. And also this the stable envelope in K theory, it depends on, so okay, maybe I'll restore K theory. Okay. So this is take this repelling directions here, and it's also the stable envelope K theory also depends. K theoretic. Stable envelope depends on a certain variable called slope, which comes from the Kähler variables in elliptics. Okay, so this have to be set. This have to be set with care, which I'm not going to do now. Need to be set with care. Chosen with care. But this care we will not do it in here in the lecture. But so here I do this map, and so here I do the same thing, but maybe more so to read it as, I'd like to read it as a map from top to bottom. So here I put the transpose of this. Is the correspondence the same thing? Means I put the stat. Means I put the transpose. This is just to read the correspondence in a way as a map from top a map from top to bottom. Then this here, so this is, we get a map here. So this map, what we've proven about properness, this is, so the theorem says what? So the theorem says about that. First of all, this is statement, the first statement, and we essentially proven that this is proper. And second, so what does this mean? This means this is here we so this means we put the repelling condition on both ends. So this is what it does. So this is proper here, and then it vanishes for a non-constant map. So this is the part. This is the part that the actual work requires. What we did today was kind of soft arguments, but then you need to, at some point, you need to really go and check. So there's some Newton polygons you have to estimate, and that's, I mean, it's not superhuman, but requires care, which of course we know it's more than one can do in the format of a lecture like that. So so you can read this is in my PCMI notes. Then this is done there, so you can read it there. But so this and so once it vanishes for non-constant maps, then we're done because what is it? What do we get? We get that stop. I recall that stop minus transpose. That is stop plus inverse. And so then what you see is that this map here is really really like a difference between stop plus and stop minus. This is the R matrix. This is the R matrix. Is stop minus inverse composed of stop plus. We get diagram of the following kind. The kind that if I take case theory of fixed locus, and then the case theory of the fixed locus, and then here I take stop plus to go to K. I believe that is correct. And if I put here my operator as sigma, here I get the QKZ. Okay, so that's how the argument goes. All right, so this is any questions about this? So this is so this implies from this one computes difference equations. Scalar variables. And this will be discussed next time. But then the question what we can ask today, and we're not going, since we can ask it 5 minutes to the end of the lecture, because we're not going to answer that, is what about the difference equation for all other so we try to find the place where I have the difference equations. So here. So what about general shifts, right? Yeah, non-minuscule shifts. So can we write difference equations for those? So what does it mean in non-minuscule shift? Means that arrow we're drawing, I just draw, it's gonna hit. So I remind you that this is like a general point here. Over that is like the fixed locus of this whole torus. And if I have a point A here, then over that sits the fixed locus of some element, of that element A. And so for in QKZ, we had a shift, which is, so we had a shift. There was X and kind of the fixed locus. So in QKZ we had a shift, and in which here we had the x itself, here we had the fixed locus, and we had a shift vector, which is, so then of course it will repeat itself. So this QKZ, the source for minuscule shift, we have this thing will go. This means we get, when we pull back this picture, we get just the lattice Z. And so this would mean X will appear periodically. And then in all other places, we get the fixed locus of sigma. And so if we shift, by 1 here, then so what we get is we get this operator. Here we get the R matrix for the sigma, which is you kind of you cross this wall. So it means you go from here to there. So it's you go from here to there. So that is the stop minus inverse stop plus, right? So this is that's the picture. And so then there's a natural conjecture that this S sigma, this is really always a product of R matrices. For all this X, for all XA. So XA is some other variety, just like so it's still an action of A, also an Okounkov variety. So there should be, so if you want this difference operator, then you take your vector by which you want to move, you see which hyperplane, which root hyperplane it crosses. So this is overall all root hyperplanes. By sigma. And so there's a good progress on this conjecture. They're putting out like a sequence of papers, which I think 2 appears. So by Andrei Okounkov, or alphabetical, I should say, Yasha Okounkov. So if Yasha was on this call, if Yasha was online, I would have asked him, how soon they can give a lecture on this. Well, Yasha is not here, so my understanding is not quite done yet, but it's to be expected. That is now this is the end of my time, and also kind of a good logical place to stop, I think. So how about questions?
You have this diagram with a sigma, which like proved that like QKZ is and I did not quite understand why the diagram is commutative. Like, was it explained? Or?
Commutative?
So
this diagram here.
No. Down, please.
But down is just rewriting of this diagram. It's just the vertical arrows. So this is what does it mean? That here I'm going to get, so vanishes for non-constant map means for constant maps, this is going to be for constant maps. We get here, with some sign Z tensor 1, Z to this one, from sine z. There's a sign which I didn't explain. Sine z to the degree, right? So that says there's a diagram like that. So if I just define this vertical arrow here, then for constant map I get something which we understand well, and for non-constant maps we get 0. And so now from this diagram we'll just rewrite definitions and arrive at this diagram, because rewriting definition means what? Means we have to somehow rename the vertical arrows, and then if we rename the vertical arrows, if we replace stub plus with stub minus with stub plus, we have to put the R matrix in. That would be. And so this is, what's happening. What's happening here is that we replace this arrow here. If we replace this arrow, that means we have to, in this side, we have to put the R matrix in, and then this R matrix is exactly what appears. That object is already, this is already inverse to stub. This is stub minus transpose inverse. So that object is already what we want. It's like the inverse. It's the inverse of that. This arrow here is the inverse of this map. But then if we want to replace this arrow, it means we have to pre-compose this with the ratio of the two, and the ratio of the two is the R matrix. That makes sense?
Yeah, thank you.
Sure. More questions? I must thank Romo for always asking a question. This is always very very satisfying to hear a question. Anybody else wants to follow Romo's example? Oh well, maybe next time. So with that's then last call for questions, or this is all for today. I thank you all for listening, and I'll see many of you in the seminar, I imagine, in an hour.